Earlier in this unit, we looked at the properties of acids and bases, and we considered things like the pH, whether it was above or below 7, whether it reacted with a metal like zinc or magnesium, and also its reactivity with its opposite, so an acid neutralizing a base and a base neutralizing acid. There's other ways that we can classify acids and bases, and if we look at the two examples here, you'll see that they seem to have different properties. So if acid A and acid B have the same concentration, but acid A seems to react more vigorously or violently or strongly, then we can classify acid A as being a strong acid and acid B as being a weak acid. A strong acid is a substance that reacts completely with water to form hydronium ions. So we've looked at dissociation and Arrhenius modified reactions before. We're going to do the same thing. If this hydrochloric acid reacts with water to form a hydronium, H3O+, and a chloride ion, Cl-, then we have the hydronium that's giving us the acid property. And because this is a strong acid, we would say it's completely reacting, or greater than 99% of the molecules are reacting with water to form hydronium. A weak acid is a substance that will only partially react with water to form hydronium. So H2SO3, sulfurous acid in water, only partially reacts, so we use a double-headed arrow, and we still write the hydronium, H3O+, because this is giving us some acidic properties, and the HSO3- that's left after that proton transfer. Sometimes you'll also see under or over these arrows less than 50%. So that's telling us that less than half of those H2SO3 molecules are reacting with water. Just by looking at the formulas of the acids, there's no way you can tell whether it's a strong or a weak acid. The good thing is that there is a table in your data booklet on page 8 and 9 that shows you which are the strong and which are the weak acids. At the top of the table, there are 6 acids listed above the gray line with hydronium. So in a grayed out line where you see H3O+, there are 6 more acids above that that are classified as strong acids. All of the other acids in that table that are below it are weak acids. So you can always look on your table to decide if something is a strong or a weak acid. There are only 6 strong acids. Everything else, even if it's not included on your table, would be classified as a weak acid. A strong base has a very similar characteristics or definition of a strong acid. So this is an ionic substance that will dissolve or dissociate completely in water to give hydroxide ions. So something like sodium hydroxide, which is a soluble ionic compound that contains the hydroxide ion, will dissociate completely to give the Na plus ion and the OH minus ion. So again, a single-headed arrow to show us that that's a complete dissociation. Any of the soluble hydroxide compounds are strong bases. Weak bases are substances that only partially react with water to form hydroxide ions. Something like ammonia, NH3, reacts with water to produce the OH minus ion and the NH4 plus ammonium ion. Again, if you look at your table, you'll notice that right at the very bottom on the right-hand side, you see OH minus. That's the hydroxide ion, and that's the only ion we consider to be a strong base. Everything else above that in the same column is a weak base. So really the only strong base is a hydroxide ion. All other bases that you might come across are weak bases. Some other classifications that you should know the definitions for include diprotic and polyprotic acids. Diprotic refer to molecules that can react twice with water to produce hydronium ions. The prefix di at the front is telling you two. The protic part is just referring to the proton or the hydrogen ion that's being transferred during that reaction with water. So in this example, carbonic acid, H2CO3, can react twice to produce two hydronium ions. In the first reaction, a hydrogen carbonate ion is produced along with the hydronium. Then that hydrogen carbonate ion can act as an acid a second time to react with another water molecule and produce carbonate and a second hydronium ion. So the two H's at the beginning of the formula are the big clue that this is a diprotic acid. Polyprotic acid is a molecule that can react more than once to produce hydroniums. Typically that means 3 or more. So poly is referring to many, and again protic means proton. So a typical example is phosphoric acid, H3PO4. For bases, we can use the same type of example, except this time we want to produce hydroxide ions. So a diprotic base is a molecule that can react or dissociate twice with water to produce hydroxide ions. An ionic compound that's diprotic is barium hydroxide, because the barium ion, which is 2+, would have two hydroxide ions with it. So both of those hydroxide would come off when it dissociates. Another example that's not an ionic compound would be the carbonate ion, CO3 2-. And you would find this in the second last column of your acid-base table on page 8 and 9. A polyprotic base is a molecule that can react or dissociate more than once with water, and again, the poly usually means 3 or more. So the phosphate ion, PO4 3-, is a typical example that you would see of a polyprotic base.